Okay, so this actually was a mysterious state. It was the first exception. To my knowledge, this is the only exception of an even denominator state in this sense. In graphene, there are other states, but they can be interpreted in a more traditional way in practice. There are other states that are not completely understood. There is a state at 12/5 and its partner at 3/5. So this is actually 5/2, which is interpreted as 2 plus 1/2. Essentially, you have the n equals 0 lambda level populated with electrons with up and down spin. And then the n equals 1 lambda level only half field. Okay, so this is 2 plus a half. And there is a question whether this is actually, for instance, 12/5, you can get that as 2 plus 2/5. So it could be a Jane state in the first lambda level. Okay. And this is, in a sense, a particle-Hall partner of it. Okay. There is another state at 7/3. Again, is 2 plus 1/3. This is, for all we know, is a Laughlin state in the first lambda level, which has some interesting additional physics associated with nematic order and things of that sort, which I will not discuss here. Okay. But these states are mysterious, particularly the one at 1/2. Okay, so here they are competing. There is a well-known competitor that will be the Jane state. Okay. So then you have to ask what is the difference between the lowest Landau level and the first Landau level. And the main difference is in the form of the single particle wave functions in the Landau level. Because as you recall from the detailed explanation that Ganpathy gave in his already first lecture, you have in the lowest Landau level, you will have the wave functions look like z to some integer times the exponential factor here. Something like that. But in the first Landau level, there are powers of z bar that you get. And that actually suppresses the amplitude of the wave function at short distances. Okay? So if you have a system with Coulomb interactions and you have a suppression, so in other words, the one particle states look like rings, essentially, with some width. And this tends to suppress the repulsion at short distances. So a suppression of repulsion can be interpreted as the existence of an attraction. So this is sort of the naive way to think about it. There's a feature of the wave functions in the first Landau level, they look like smoke rings in this sense. And so the physics is somewhat different because of that. Aside from that, we're going to treat it as if they were in the lowest Landau level, as you will see in a moment. The wave functions look the same. Some features actually, in principle, some of these states that have been proposed, in particular for perhaps could in principle exist in the lowest Landau level, and I will explain later why. But they have never been observed. Okay. So in order to understand the new proposed states, and these are the so-called non-Abelian states, as you can see, there aren't so many of them. Okay, but in principle, there could be more. There was a paper that was loosely inspired by this, but was more inspired by a mathematical structure, in a sense. Okay. By the way, I don't know how many of you know, John Cardy and Sasha Samolozhikov were awarded the 2024 Breakthrough Prize. I just learned that, which is, it beats the Nobel Prize money-wise. It's said to be the blingiest or the blingiest of the prizes because it's a more, let's say, substantial, and maybe it doesn't have the history of the Nobel Prize, but it's actually for their work in conformal field theory and its applications in 2 dimensions. Okay, and this has have a huge impact to the things that we do here. Okay, this is directly, so we have to thank our gods, Cardi and Samologikov, for a lot of the things we understand. Okay, I tried to send John a congratulatory message, but he's emeritus from one place, went to some other place. I'm not sure where he's now. Okay, so I have been trying to reach him. Okay, aside from that, okay. So there is a paper by these. Some of these ideas were discussed before by other people, but not as serious. Not they didn't take it seriously. This Moore is not Joel Moore. This is Greg Moore. He's a string theorist or mathematical physicist, you might say, and Nick Reed. You can see that there's some crossovers going on here. In fact, the breakthrough prize is precisely for the impact of ideas of field theory have in other areas, such as our area and vice versa. It's actually explicitly stated in the prize. Okay, so this is the wonderful example of this. So they looked at the Laughlin wave function, we call it psi m, of all these z's. Times the exponential factors. And they realized that you can write this as a correlator in a 2-dimensional Euclidean conformal field theory. You will see that this Euclidean conformal field theory will look suspiciously familiar to you in a moment. Let me tell you a personal anecdote. Back in 1983, this is before the string theory explosion, we used to have, and we still do, but because of COVID, it got interrupted, a joint seminar with the University of Chicago. And so we live 200 kilometers apart, so we just, we travel and they come, and we go. And we had 2 talks. A talk by Wu-Pei Su of Su-Schrieffer-Higer, who was a postdoc, and he wrote the Laughlin wave function in his talk on the blackboard. And the next speaker was Dan Friedan, who was already working in string theory, essentially in the so-called Polyakov string. And he wrote this something called the Veneziano amplitude, which is an amplitude in the old string theory before string theory became a revolution. This is from the late 1960s. And we looked at the expressions and they were the same, essentially. And we had a long discussion with Leo Kadanov, with Yoshiro Nambu, and a bunch of us, and Steve Schenker, and, and Dan Friedan. Is this an accident, or is there something behind it? And we couldn't decide at the time if it was an accident or was something deep. These ideas that these people were the ones to actually make it more solidly were rediscovered by others, in particular by a group around Sergio Fubini. Slightly, before this work is 1991. And they also, because Fubini was an old stringer, so he knew vertex operators because he invented them. Well, him and Virasoro actually invented them. And so they realized that this close mathematical connection between them, but there was no reason to understand why this was so. The connection, of course, comes from the connection with Chern-Simons theory, as we discussed in these lectures, from the mathematical point of view. And this is thanks to the work of Witten. Okay, so what these people showed is they said, let me write, and actually, I'm going to change the normalization that I use in the past lectures only because of the normalization that is used in this paper. So if you read them, you will not get confused if you read them. So you can rewrite this expression in the following way. again, up to a normalization as a correlator in a Euclidean. Remember, Euclidean means imaginary time, two-dimensional CFT, conformal field theory, which is what we're going to call U1 level M, as we did before. So it looks like the same theories, but we're going to, it's like the theory of the edge that I discussed before, but in imaginary time. You will see that it plays a role in understanding the wave function. So this is a product from 1 to n of e to the I square root of m phi of ci, and then this exponential factor is a factor of root m, the areal density, this is the areal density, times phi z prime, calculated in this theory. So it's the same theory that we have been using to describe the edge. You go to imaginary time, and then you use it to write the wave function as a correlator of that theory. Okay? So sometimes people call it the CFT of the wave function, if you wish. But you can see this is related to essentially the correspondence between the bulk and the boundary. But the only thing that you have to be careful is that this is an imaginary time. This term here is essentially, if you were to compute just this, so this is essentially the electron operator. Which before I wrote it as e to the I m phi, this factor of square root that these people use. So this is a U1 level m with a compactification radius that is not 1 but root m because of this rescaling. With root m. Yes. So the compactification radius is root m. It's a rescaling of the field. That's all there is to it. So in a sense, there was a factor of m in front of the Lagrangian. You rescale the field, and then it shows up, it disappears from there, it shows up in the compactification rate. Okay? So essentially, you are inserting n electron operators, if you wish. That's really what you're doing here. But this thing is not invariant under global shifts. So because this is, there aren't as many electrons as holes. So this will vanish. So you need a neutralizing background to cancel this charge, this total charge. And this is what gives you the this exponential factor. So when you do this computation, this term here essentially will give you this, and the interaction between these two terms gives you the exponential factor. That's how it least works. Okay. So in this language, the electron operator then is e to the I root m phi. The quasi-particle operator is a vertex, another vertex operator. Again, up to, I'm not going to include here Klein factors and all of that. Some people love them, I don't, but here they are necessary. And there are some normalizations. But here, the fundamental quasi-particle is e to the I phi. Again, this is done in complex coordinates over root m. So notice this. This object has scale. Let me have here the scaling dimensions. So this tells you how the correlation function decays. Okay. The scaling dimension for the electron is m over 2, and if m is odd, the correlation function is is 1 over z to the mth power, which is odd, so you have a correct behavior. And for the quasi-particle, for the fundamental quasi-particle, is 1 over 2m, And there is this duality here between them, which we discussed briefly last time. And there are only essentially m possible quasi-particles, essentially ranging from, let me call them v quasi-particle to some power n. So essentially it's e to the I n phi of z over root m, and n will be 0, 1, up to m minus 1. So 0 is the identity operator which is included here. So there are, as we discussed last time, there are m quasi-particle types. This is what corresponds precisely to the Laflen's flux tube insertions. Okay, so you can write them in this language. Okay, I'm not going to go through all of this, but you see that there is it's essentially the same construction. The only thing that the CFT that is used is in imaginary time. So it looks like two-dimensional statistical mechanics in that language. Okay. Well, not quite, but in the sense that it's imaginary time. Okay, so Moore and Reed then, understanding this, said, well, maybe we can actually extend this idea to other possible wave functions. And Moore, with Nati Seiberg, essentially developed a theory of so-called extended symmetry algebras, which came directly from conformal field theory. And they showed that the correlators in the conformal field theory can be decomposed. I'm not going to go through the math, between a holomorphic or right moving part, an analytic or right moving part, and anti-analytic or left moving part. In other words, a function of z or a function of z bar. And these so-called conformal blocks can be used to essentially construct wave functions. The existence of these conformal blocks is closely related to what I mentioned before, but it will be important today. These are the so-called fusion rules that appear here. And the conformal blocks contain branch cuts. So these wave functions have, in the mathematical sense, called something a monodromy. So if you take one of the coordinates and you go around another coordinate, then you get phase factors as you do this. But here you get more than phase factors, you get linear combinations of these other so-called conformal blocks. So we're going to see how that works in this context. So what they proposed, this is the so-called Moore-Reed states. This is large enough, by the way. Okay, so the Moore-Reed states, again, are functions of n complex coordinates, as usual. But it involves a quantity called the Pfaffian. Times the Laughlin factor. To some power, let me call it n. And the usual exponential factor. It's already here. I don't need to. Okay. So this looks like a Laughlin with an index n, not m. Well, it's the same as Laughlin. What is a Pfaffian? Well, when you were in elementary school, you were told about determinants. So determinant, you have a matrix, okay? And you can compute the determinant. The Pfaffian, including its sign, is the square root of the determinant. That's what the Pfaffian is. You will see that this has a lot to do with a process we are going to call pairing, okay, which is hiding in this state. So you can see that this looks like it's going to have a bunch of poles. Now, when the two particles come together, this actually appears to have a pole. This appears to blow up, but these are the same coordinates, and n is not 0. And so there is a cancellation of that singularity. But because of this factor here, the particles, electrons, can be closer together than otherwise they would have been if you were in a Laughlin state. Okay? So this actually allows for a more dense version, if you wish. It's more dense than the Laughlin state in this sense, because electrons can be closer together. Okay? Yes. Can't hear you.
You have written something Pfaffian of 1 by Zi minus Zj.
Yes.
I mean, which Ij is it? Or is
It's
it?
all of them. It's a matrix.
Okay.
Call it Mij, whose matrix elements are 1 over Zi minus Zj.
Okay.
Instead of computing a determinant, they compute the Pfaffi, which is a square root of the determinant.
Okay. Okay.
Roughly, I mean, the other way is to write it, but it's true. There's a sign question that is important. Okay. We will see, perhaps, if I get to that today, that this is related to wave functions of a certain superconductor that breaks time reversal symmetry, called the P plus IP superconductor. We'll mention that later. Okay, and so what I need to do is, okay, this part I know how to write. I need a chiral boson, okay? And this index n, by the way, for this to be a fermion, n has to be even now, because this guy is odd. So n even, the fermions, for a fermionic state, n is even. And for bosons, n is odd. And the reason is because this guy is odd. And so the rule that we had before gets switched. Okay. So you can write this in the following way. Suppose I give you a theory of, it's a 2D conformal field theory in a sense of Majorana chiral. I'm going to write the Lagrangian in a while. And as you learn in second grade, Majorana is important for the solution of the Ising model. Okay, so the solution of the...
We had Landau
Yes, in second grade, not chiral necessarily, but the Majorana. So when you take the Ising mode, you write it as a transfer matrix, or you write the one-dimensional quantum chain, which is the same. You do this Jordan-Wigner transformation that maps essentially spins to fermions. The fermions that you get are actually Majorana. They are real fermions, meaning that they satisfy the property that chi dagger is equal to chi. These are not Majorana zero modes. Okay, these are actual things that propagate. Okay. In fact, the excitations of any superconductor are like this. Any superconductor. They don't have to be bound states of anybody. Because in a superconductor, the excitations, the Liouville quasiparticles that you might have heard, do not have charge because the charge is eaten by the condensate. This was shown by Rambo in 1959, I think, something like that, that they are actually self-adjoint. They are not Dirac, they are Majorana. So in this language, the Pfaffian factor of 1 over Zi minus Zj is written, and these guys are free, by the way, it's going to see, as chi of Z1, chi of Zn, is that the correlator of two chi's. So these are complex coordinates. is up to a normalization, a simple pole. So they are fermions in that sense, okay? But they are, quote, real fermions because they are self-adjoint. So I mentioned Ising because this is going to be important in what we are going to do next. This theory, in the sense of free Majorana fermions, is actually the conformal field theory of the critical point of the Ising mode. It's usually called the Ising CFT. But it's usually written not in terms of Ising spins, but in terms of this fellow. Okay, so on the other hand, so this actually, as you can see, because of that, because these fields are free, you can do essentially the weak, as in this guy, contraction, so you can decompose the expectation value of the product into products of pairs in all possible orders with signs included. And this gives you that. Okay, so the Pfaffian is just that. So that's how that works. So this is just, because these are free fields, you can do just the, okay, if this were Dirac, this would have been a determinant. So if the fermions were not self-adjoint, but the chi dagger was different from chi, then you will get a determinant. Okay, this is otherwise known as a Slater determinant sometimes for some people. Okay, it's just a determinant. So here is the square root of that. Because like Majorana is half of the Dirac fermi, it's like a real part. Okay, so on the other hand, this guy, we know how to write it. We just did. Is this. Okay, so the Moore Reed state, therefore, in its full glory, is a correlator that now involves the product over I going from 1 to n of chi of zi e to the I root n phi I times the exponential factor that we have, the neutralizing factor that only affects phi. Okay, is that factor. And because this is in a sense a product, you compute these two independently, even though the coordinates are have to be glued together. Okay. Now, because of that, you can see that the filling fraction, you can read it off from here, is 1 over n. And you see that the electron, the good old electron operator at say some location z, is essentially chi of z times e to the I root n phi of z. Now we know what the scaling dimension of this guy is. It's essentially n over 2. And this guy, if you stare at that, it tells you that the dimension of this guy for chi is 1/2, is half of the exponent. Okay, plus 1/2. This is n plus 1 over 2, which is an odd number divided by 2. So the correlators of these things are proper Fermi. So they look like an electron in that sense. So the fermionic character, in a sense, comes from here. Otherwise, this will be a boson. Okay, so this is a form of, quote, fractionalization, if you wish, that is popular in some places. So there are two states of interest. The state for nu equals 1/2, which is n equals 2 in this language, which is the state that is related to what is observed. And there is actually a relative of that. So this is a fermionic state for n equals 1 for bosons. So why is that bosonic? Because if n is 1, this is odd, and this is odd, so the whole thing is even. So it's a bosonic wave function. Okay? And then these guys showed that in fact there is an ultra-local projected into the Landau level. There is an ultra-local Hamiltonian for which this is the exact ground state, but it's a state that involves three body interactions. It's not two body interactions. It's an example of what we nowadays call a cluster state because of that. It involves three particles at a time. Now, the bosonic case has never been seen. There are various proposals for this in some spin liquids, but we always say, well, if we cannot do it in a solid state device, I'm sure that the cold atoms people can do it, which is false. They try to do it by using what is called a rotating trap, and it turns out that the trap breaks apart before they get to this regime. Mathematically, I mean, as a model, you can do it, but there are practical problems associated with the shape of the trap and all of that. And these guys actually don't like to work for too long on the same problem. So they basically quit. They had other fruit to take care of. Okay, so this is what the wave function here is. Let me tell you what the edge structure of this problem is. Okay, so you see that there is if you want, there is a dictionary that tells you how to go from the bulk to the edge from this language. Now there is a state that I will not have time to discuss, so you can get all excited and say, well, what if instead of this simple wave function, this simple CFT, so this is a free Majorana CFT and a free boson CFT, I can replace Majorana by something more exotic. Okay? And the more exotic is called a parafermion. And there are CFTs that involve parafermion states. They are loosely related. Originally, this was, I think I explained that before. The name, unfortunately, is due to me and Leo Kadanoff. We were looking at clock models in two-dimensional statistical mechanics. And for instance, the three-state clock model has a non-trivial CFT. And the three, this was solved by Zamolodchikov, actually, and others. And in that case, you actually find this parafermion there. So you replace the Majorana with this parafermion, and then you get a very rich state. And that's a state that people think might occur at 12 fifths. So it's a candidate. So the competitor of Jane is me, I suppose. Is a parafermion, not me, but Zamolodchikov, actually, in the sense of the CFT. Okay, so for 12 fifths, okay, which will be the 2 fifths so-called parafermion state, this was proposed by Nick Reed and Ed Rezai in 1999. You can see that they're like decades going from one thing to another. Okay, we'll not have time in these lectures to actually discuss this. Okay, so let me tell you about the edge structure. And I will tell you now why this is called actually the Ising CFT and why that is important for this. Yes. Sorry? Yes, I know, but I need space and I don't want to use periodic boundary condition. So I need space. I know that. Everything. Okay, so the edge states. The more read state, which is the simplest of all of this. Okay. So as you saw, has a charge mode which essentially we're going to have a charge mode, which is going to be in the edge version of this guy, which is now going to be in the real-time signature, okay, because we have a quantum theory at the edge. Okay, it's not done in the Euclidean signature. And we're going to have these guys. So there is a charge mode. So this is already telling us that this state is going to have a neutral mode, and the neutral mode is going to be a Majorana. So we already know this from here. So you see, either from the structure of the wave function, you can construct the edge, or if I know how to construct the edge, I can construct the wave function. So it's a two-way street, assuming that there is nothing perverse such as edge reconstruction, which I will ignore and know this order, please. Okay. So there is a charge mode. Which will be this field phi of x, and here x will be time and space. Okay. And because of the normalization that I am using, there is no factor of n here in front, but you get just this. It's just that. Okay. So remember, we used to have a factor of m here for Laughlin. I rescaled phi to absorb this, so you don't see it here. So it's compactified, the compactification radius occurred. R is the square root of n. Whereas before it was 1, and the rescaling did just that. Okay. So the allowed quasi-particles, let me just put the p here, will be an index which I'm going to call little p, but it's not for quasi-particle, but it's an integer. It's going to be a vertex operator, p I of z over, well, phi not of z of x being that over the square root of n. And this guy has, as before, delta, the scaling dimension p is now p squared over 2n. Okay, so this, you need to truncate the series as before. Okay. Now this theory has something that is called a central charge. The central charge is, I'm not going to go into this, it's called C. Is related to the correlation function of the energy momentum tensor, which is energy and momentum of this edge theory, this conformal field theory. Instead of having simple correlators, they have what is called an anomalous part. And the central charge C appears there. It's a very important number because it tells you, for instance, it controls the heat capacity, for example, of these one-dimensional systems, including our edge states. Okay, so the usual formula, for instance, the Stefan-Boltzmann law that says that the heat capacity in one dimension will go like T squared times some coefficient here. That coefficient here now includes C. It's a factor of pi over 6, and so on. And actually, this is due to Cardy. This work is one of the things that Cardy did. So this number C, in this particular case, C, the central charge is 1. And the electron we saw has the factor root n upstairs. Okay. Now there is another, let me talk about the neutral mode. For those of you that like Star Trek, is neutral zone, okay, I guess in that case, is the Majorana field. is a chiral. And the Lagrangian looks like chi I d naught, the time derivative of chi, minus the velocity of the neutron mode I d1. Notice that there is no dagger here. Okay. Normally we have written a dagger on the left field. That's because it's our Majorana. Okay, so this is free, it's a free theory. In principle, there are two different velocities, and this matters for the operation of the interferometers and things like that, because typically, as before, the charge mode is faster than the neutral mode when you do microscopic calculation. So this guy chi, the scaling dimension, as we noted before, because as a simple pole as we did before, is 1/2. And the central charge is also 1/2 because it's half of a Dirac fermion, which has central charge 1. There is this bosonization formula that relates a Dirac fermion to this compactified boson. So this being half of that, you get half of the central charge. And when you compute, say, for example, the heat capacity or the ground state, the Casimir energy in the one-dimensional Ising chain, then you find that C is 1/2. This also plays a very important role in the computation of the entanglement entropy. In these one-dimensional systems, is usually the famous logarithmic factor of the region that is being observed, and the prefactor essentially includes C. Now, I have 1/2 coming from here, 1/2, sorry, 1 coming from here, and 1/2 coming from there. That means that the total C is C for the boson plus C for the Majorana, so it's 3/2. Okay. And this is actually measured in thermal conductance or conductivity. Someone corrected me the other day when I said it was conductivity, but it's conductance. This, people like Murthy has done quite a bit of work in that area. These are difficult and challenging experiments, and they have measured this. Now, this is a matter of controversy. There's a question. There are other possible states you can write. There's something called the anti-Pfaffian, which is the particle Hall conjugate of this. There's a particle Hall Pfaffian. They're not even conjugate Pfaffian, your mother's Pfaffian. There are various things that are being, I'm told that I missed a lecture by, I think, Mandal, who has another proposal for this. So there are many other proposals. This is the simplest. And it seems that in graphene, this is the one that works, but in gallium arsenide, the anti-Pfaffian appears to be the one that works, except that Murthy disagrees with all of that. And he says that only the particle Hall Pfaffian works. And this is not a settled problem. Notice that this is a fully polarized state. There is no spin here. And that was a mystery for a long time. People thought that maybe this was partially polarized, and it took a long time to settle this. I think the evidence now is that this is a polarized state. Okay. Now, in principle, you could say, well, just take the product. So what are the possible anyons that you could have? I could make all of the anyons of this. I have the Majorana. Maybe I can put them together to a tensor product, because after all, the theories are free. Yes.
I have a question, Eduardo. So you have your wave function.
Yeah.
Just from the wave function, how can you tell that the boson is charged, but the Majorana is neutral?
Essentially because this is what gives you the filling fraction by using your argument. If you look at the highest angular momentum state, it comes entirely from that. It's essentially the same argument that you use. So that's how you see the filling fraction. From the point of view of the edge, what you need to do is to couple this to a gauge field, the vector field, and then it only couples to that because it's a neutral. You cannot. That will come. Well, I'm going to come. The Chern-Simons theory here is more complicated. It's non-Abelian. I'm not going to get into all of that. This is the reason why Witten got the Fields Medal due to the 1989 work. It's a beautiful paper, but it's beyond the scope of these lectures. I will just tell you some things and not more than that. Okay, have time. Okay, I'm going too slowly, but okay. So what are the observables? Okay. I'm constructing them at the edge, but then you can translate down in the bulk. I will tell you how to write down, or people have written down the quasi-Hall wave functions. In fact, up to 4 quasi-Hall wave functions. We know exactly what the wave function is, up to 4 quasi-Hall states. So the electron, as I mentioned before, is just this. So it has a scaling dimension, 1/2. It has charge E or minus E, depending how you think about it. Okay, and depending where n is even or not, this is a boson or a fermion. Okay, so I will have that. But this is not a quasi-particle. Technically, actually, I want you to notice the following. I have a theory of, at the edge, of free Majorana fermions and free compactified bosons. Let me assume that I ignore the difference in the velocity. There clearly is some kind of symmetry between the fermions and the bosons. So in 1987, Willett and Eisenstein discovered supersymmetry without knowing it. This is actually a supersymmetric state. Okay? It has this hidden supersymmetry in it. So you don't need to go to the LHC. Sorry for those who like to do that. And this, I'm just like to tease my particle physics friends. Okay, about this. But this theory has supersymmetry. It's special in that. And the supersymmetry is manifest in the fact that the allowed states have to be, as we normally say, local respect to the electron. In other words, have trivial braiding relative to this guy. And this actually acts as a selection rule for what states you can write. It's not just a tensor product. Okay? So the only states you can write, in other words, the only anyons you can write have to be local respect to the electron because the electron is the fluid. Okay, it's an electron fluid. Okay, so this is what sometimes is called an extended symmetry algebra. That's what Moore and Reed did. Okay, so that's an important condition. So this is the electron operator. Sometimes it's called a current in this language, but forget that. Okay? It's not a current in our language. Okay, then we're going to have states. So the quasi-particle is going to be the Majorana itself. That guy. Okay. And we know what the scaling dimension is. And we are also going to have the Laughlin quasi-particles, which are this e to the I p phi over n, okay, which we just is this all there is? This is the question. Is this the full list or there is more? So these are the, okay, I'm sorry. I wrote my observables here. Okay, so let me erase some of that. Well, it turns out there is an object, and actually this guy has charge 0, and this has charge p over 2n, or p over n times e. This is what you expect. Now, this CFT that results is sometimes called Ising or Ising times, so Ising times U1 at some level. It's just a name of it. So now we need to investigate the role of the order parameter of the Ising model, how that relates to my Majorana. Let me look at the so-called Ising canyon, which people normally call the Majorana zero mode incorrectly. That's a mean field construct. Okay, and it essentially it masks the actual character of this n. So there is another one. Let me call, in the Ising mode, we have an order parameter. Let me talk to the Ising CFT, just to understand this. So it has a primary field, which is the order parameter. The honest to God, I'm going to call sigma for that reason. And in the Ising model, it turns out that the correlator, let me go back to Euclidean space, so you write this in terms of Z and Z bar now. W bar. This is up to normalization, Z minus W to the 116 to the 31/8. C bar minus W bar 1/8. So this is for the usual Ising model. And then what we do is you only keep that part, the right moving part, the analytic part. And that tells you that the scaling dimension for sigma is actually 116. It's half of this exponent. So this is a famous exponent. It's related to the exponent of the magnetization as you go approach the critical point. Okay, so this is, and the Ising CFT has a number. If you take two of these guys and you fuse them together, which is to say two of them, and they approach each other, they can approach into the identity. In other words, at long distances, two of these guys can look like nothing, or they can look in the full theory, in the usual Ising model will be the energy density, but in this language, it's just chi. Whereas if you take two of my, we call it VP and V prime, essentially they look like VP plus P prime mod n. If you approach two of these more the so-called abelian vertex operators associated with these usual Laughlin type objects, so they are simply, charges are additive mod n. Mod n because there is this truncation. But there is only one channel, as we say. Okay, there's only one channel here. Okay, and you can also show that chi with chi is the identity, which is like saying chi square is identity. So at long distances, it's the same as nothing. So these are the fusion rules of the so-called chiral part of the Ising CFT. And these are the fusion rules for our Laughlin guys. Yes, it's the Majorana. Because it's a technical question. So if you work in the for the full Ising model, which has both right and left, will be the energy operator, which can be written as chi right times chi left. Times a factor of I, which we will not discuss here. But let me not get into that. Okay. So now there are two channels. Okay, so I want to know if I can make a quasi-particle for these guys based on my Ising field. And one important property of sigma is said to twist chi, in the sense that if you have a theory where chi has periodic boundary conditions and you insert the sigma operator, then it becomes anti-periodic. So it changes the boundary conditions of the formula. Let me finish. This is the important part. I want to stop here. Ask me later in a moment. Okay? So this led to the proposal, which is what Moore and Reed proposed, to do the following. So they say, well, instead of working with the Laughlin quasi-particles that essentially have this nice property, they propose to use a, what I'm going to call, they call the half vortex. Which is essentially e to the I of x over 2 root n. The problem with this is that this is a double valued. That's why it's not allowed on its own. But chi is also double valued because it's a fermion. Okay? And so is sigma because of this property. So they proposed to have this to be the operator, I of x, or if you want in the wave function. So this is the Ising. So this is what we're going to call the Ising union. In the Ising CFT is just sigma. And the charge part here comes from that. So the charge is still going to be E over 2n for general n. But the scaling dimension for this guy is going to be 116, which is the dimension of this, plus the dimension of that. But notice there is a factor of 2 here in the denominator. But that gives you 1 over 8n. So for n equals 2, then I'm going to write a little table in a moment. Okay, maybe that's what I will do now. I have my table. Okay, so given the time, I think I will do that. Okay, so let me write here a table. I'm going to have the identity operator, sigma e to the I pi over 2, which will correspond to the case of, well, okay, in this notation. Oh, this is for nu equals, sorry, this is nu. Okay, this will be, well, let me not do that. I have a table for the another state. So if n is 2, you see this is 116, so you get 1/8. Okay, so that's what there is. So the important question is, okay, so now you have another possible candidate that is allowed in this theory. And it's not, in some sense, it's not a tensor product. This is local respect to the electron, so it satisfies one of these rules. Let me tell you what the, okay, you ask your question, and then I'll tell you what the wave function is.
I think that my question was a table, because what I wanted to ask is, you know, what are the real types of your fusion category for this case?
The what?
The types. For the types for the fusion category that you
This
have
is
here.
called the Moore-Reed state. This is the fusion category. Let me not get it. We'll talk about that later, what the MTG or MTT, whatever it's called.
Okay.
Okay, it is one of the allowed ones. This is related to SU2 level 2. It's not quite the same as the deformation of it, SU2 level 2. We'll talk about it. Maybe if I have time, I will mention. So it's related to SU2 level 2 Chern-Simons theory. Okay, so.
Question.
Yes.
So when we discussed these wave function, we reinterpreted them in terms of these Majorana operators
Yes.
and the corresponding phi operators. I'm trying to understand where the Ising CFT
I'm
came
going
from.
to see that now, precisely. I'm going to write down the wave function that includes now insertions of these Ising, these more read, sometimes called non-abelians, which are these things. Okay. That's precisely what I'll do now. This is something that Moore and Reed didn't quite do, but it was done a few years later by Chetan Nayak and Frank Wilczek. This was part of Nayak's thesis. So this is Nayak, Wilczek, around 1995, I believe. Okay, so they said they want to write two quasi-Hall of these types. Darker, I have to write double, okay? So the problem is that they are tiny yellow charts, okay? Where? Is there a yellow chart here? They're slightly bigger, marginally bigger, okay? I'll tell you later why I don't use small chalk, but not now. Psi for two quasi-Halls, say at two locations. What do you mean? Red, blue? Okay, it's even smaller, come on. Two quasi-Halls, okay? So they propose to do the following. So this is the analog of Laughlin going to do these insertions. So I1 to N, this will be the electron operator here. The level of the wave function, we now go back to Euclidean space to write it. I of the I, so these are the electron operators. And then you have a product, 1 and 2, if I have only two, sigma, some locations, let me call VI and V1 and V2, e to the I over 2 root n phi VI times the exponential factor that neutralizes these phi's. And this is computed in this tensor product theory. Okay? But notice that I need to have the sigma. So I have to tell you. So the location of the quasi-Halls are at points which I will call V1 and V2 are 2 points. Here, if I want to have 4 of them, I will have 4 inserts, so it will be up to 4 of this. Okay? So what Nayak and Wilczek realized that the way you do this, okay, so you're going to have the way you do this, so the part of the associated with this compactified boson is the traditional one. Okay. The question is how you deal with the chi's and the sigmas. Okay. And so what they did is to say what you need to do is you modify the Pfaffian, which looks like this, and it becomes another Pfaffian. Where you put here, say, Zi minus Vi, Zj minus Vj, plus the same thing with I and J exchange. It will be Zi minus Vj and Zj minus V. Sorry, this will be 1 and 2. This will be, thank you, will be 2, and then this will be 2 and 1. Thank you very much. That's how it works. Okay. So you can do this this computation takes some work, but there's a lot of algebra here to do this thing. So they calculated essentially this correlator, and you obtain something simple. The case that is more important is what about if I have 4 quasi-holes? Okay. You can do the same. There will be allocations V1, V2, V3, and V4. And you notice that actually you're going to have these branch cuts running around now, because I have these half vortices. So they don't have integer power, so they have square roots in there. Okay, so what they showed, and I'm not going to do that for you. So if you take 4 locations, we call them V1, V2, V3, and V4, you have to decide how you're going to put your branch cuts. And it turns out there is more than one way to do that. In other words, the location of the quasi-holes, which are here, does not specify the actual state. There are several possible states. And there are 2 that are linearly independent for 4 of them. Okay, so for instance, I can run my branch cuts. And since they are branch cuts, they will go in blue. For instance, I can pair them this way, or I can pair them that way. You could say, well, what about pairing them across? It turns out that they are not linearly independent. So these 2 states, or the other one, if you don't have this, span a 2-dimensional Hilbert space. So let me call this state 1 and state 2. And notice that, so there is a 2-dimensional Hilbert space. It's a qubit. This is what people call a topological qubit. Okay? And so if you are deep in this topological limit, they are degenerate. Okay? In fact, in this limit, they have 0 energy. Okay? But we can negotiate the energy. So they have whatever energy they have. They are very far from each other. In fact, the way you calculate many of these things is by using these fusions. And then you can compute this correlate. Now you can ask yourself, what is the statistics of this? I told you what the scaling dimensions are, what the charge is, and so on. But we want to know the fractional statistics. When you say, well, the phi fields will normally give you fractional statistics, what do you get here? So if I do a braiding, for instance, I braid 1 and 2, in other words, I take this guy around the other halfway. What you do is you don't get back to the state 1, but to a linear combination of between 1 and 2. That's what they showed. Okay. And in fact, they showed they have a beautiful argument where they can classify this for an arbitrary number to what the degeneracy is. And they showed that the dimension, if you have R quasi-holes, this y, we call this thing, quasi-holes, R of them. The dimension of the Hilbert space is 2 to the R minus 1. So there is some kind of entropy here, because there is a large degeneracy. The degeneracy grows exponentially with the number of insertions of these guys, the number of quasi-holes. For large R, notice, sorry, this is 2R, sorry, it's 2R of them. It's important, this factor of 2 is very important, because I have to pair them up. They have to be an even number. So for R equals 1, there will be 2, for R equals 2, there will be 4, etc. So for large R, this goes like square root of 2 to R. Sorry, to the 2R. Just a moment, let me finish this point. So it is as if you had an entropy of square root of log square root of 2 per quote, vortex. It's not log of an integer, okay? And the fact that there are two of them, this is essentially the fusion rules in action. Because when you do this computation, you will end up with two essentially channels, as we call them. And when you fuse them pairwise, you will get either the identity, which will be a simple correlator, or a chi. And then you keep going. Okay, so this essentially is what a non-abelian state is, and it's non-abelian because let me tell you what the statistics is. Now there will be a linear, because I have a linear combination of this when I actually braid one around the other. So there will be a unitary matrix that characterizes that process. And that matrix, and this is also what they showed in that paper, is, well, up to factors of √2. It's an e to the I pi over 4 here. But there is a matrix. And matrices don't commute. So if you do this, say you take a collection of, a certain 16 of these guys, and you begin to do braiding operations, they don't commute. That's why it's called a non-abelian ennian. Okay? So you may want to have these matrices to span the entire so-called block sphere, for people in the audience interested in quantum information. This is actually not quite complete. This doesn't quite work. For that, you need some additional so-called gate or field to complete that, which spoils the topological protection. But these things are, aside from that problem, the topological protection comes from the fact that these are not internal degrees of freedom, and therefore no local perturbations can actually affect this, because this is a distributed state. Okay? So that's why we love these states. Now, unfortunately, we're not going to get a topological quantum iPad anytime soon, because based on this, even if I solve the problem of universality, the universal quantum computation problem, I will need a very large magnetic field like 10 Tesla. I need to go to the millikelvin range, and it will be hard to carry this around. Okay, so this is why the people that actually want to make these things into actual qubits that they can use in a quantum computer don't like this platform, but this is the only one that works as well. There is yet no proof experimental for this, but we know that these things have to be there. We know everything else about this state. And nowadays with graphene, where this state also exists, the 2D is exposed. So you can actually go with STM and carry them around. So Andrea Young in particular has some wonderful proposals to actually study fusion there. Okay, so you can see how that works. So this is work that is still being done today, even though the papers, as you can see, they're from 30 years ago. Okay, so what time I have? What? I have 9 minutes. Good. Okay. So let me tell you. So you had a question, I thought. Okay, I had in my notes. I have more technical details, which I skipped here.
Eduardo, quick question. I mean, on your historical perspective, I mean, there are different ways of connecting these Majoranas to Ising-like models. And for me, I mean, one of the simplest one is to play directly with the Ising model, and then with its spin and disorder operators. Yeah. It's a hands-on approach, and then you eventually see your Majorana.
This is fine. I do it the same.
No, let me first ask the question before. Yeah. Now, personally, when I try to read all this quantum Hall stuff, it always struck me as somewhat complicated. I mean,
so can we discuss this later? Because there are a couple of things I want to say before I end.
Sure. Yeah.
That I think is important, but I have a few minutes only.
Okay. Sure.
Okay. So maybe you can ask me the question after I end. Okay. Thank you. Okay, so Gerardo wanted to know what the modular tensor category is for this problem. This is strongly I don't have time to go over this, but this is related to SU2 level N Chern-Simons theory. In fact, this is not quite what this is. It's a deformation of this. But for the bosonic state at nu equals 1 is actually SU2 level 2, and I have an explicit construction in my notes. And you can see from the edge that, so you can construct, you can show that because it's SU2, you expect to see 3 currents because SU2 has 3 generators. It's not just one charge current. So there will be 3 currents, the usual charge current, plus 2 others. And you can show that they satisfy the Kac-Moody algebra for SU2 level 2. And then you can show that this is actually using Witten's work. This is essentially the edge of SU2 level 2 Chern-Simons theory. For this case, it's a deformation of that. It's what is called a coset model. And the actual category is a coset that you need to construct. Okay, that's what it is. Now, let me finish with 2 things. Let me talk about, 2 comments. One comment is pairing. So let me use the law of conservation of Pfaffians. And these ideas existed for quite some time, but there's a beautiful paper by Reed and Green, 2000 around or 1, something like that, which do this quite explicitly. So they look at the BCS theory of a Px plus I Py superconductor. So this is a relative of helium-3, projected into 2 dimensions. Helium-3 is a triplet state, and then you put the so-called D vector perpendicular to the surface, and you get this state coming from the so-called A phase of helium-3. Okay, so it turns out when you go through this construction, so this is an angular momentum 1 state. And in principle, even without having attractive interactions, there's an old argument by Kohn and somebody else, I forgot, that even with repulsive interactions, you can get essentially, Kohn-Lattinger, you can get a pair state. They did a mistake in their calculation. They estimated that the usual critical temperature will be sub-microkelvin. It turns out that you can easily get things of the order of a Kelvin orbit. So there was a mistake in the calculation. So in principle, you could get it even in the lowest lambda level without an explicit attraction, even with repulsive interaction. But there are other things which are more robust, and for that reason, probably doesn't happen. For instance, the compressible state, perhaps at very low temperature, can actually have a phase transition to this, for all I can tell. There is no proof that this doesn't happen. Okay, and then you ask, what is the BCS? There are 2 regimes here. There is something called weak pairing, which is essentially the BCS regime. You might have heard of the so-called BCS to BC crossover. It is not a crossover, it's a phase transition. You could go to the regime where the Cooper pairs are actually tightly bound. Then you get actually a state that is an abelian state, was proposed by Halperin actually in the mid-80s. So there is a phase transition between this P plus IP state and this sort of simple Halperin state. In BCS theory, this happens when the chemical potential falls below the lower bound of the band. So you go to this real space bound state. Okay. So what Reed and Green did, and there is a quote in Schrieffer's book on superconductivity thanking Dyson, and Wilczek and others usually refer to Dyson for this. Dyson came to visit Urbana, the math department. My colleague Mike Stone asked him, "Have you done this?" I said, "I don't recall, have I ever done that?" So for that reason, I quote Reed and Green, who do it explicitly. And they show that the long distance form of the pair wave function for Cooper pairs in this weak pairing regime is precisely this Pfaffy. Okay. The way we think about this, and this is one way, and this is all model dependent, uses some sort of mean field theory, and that's what they did. Essentially, you think of the composite fermions, which for me are the same as the Chern-Simons ones, but not for our distinguished chair, that you could actually have an effective pairing interaction between them. We can negotiate what the cost of that interaction is. It could be the Chern-Simons gauge fields or many other things that are around. So you can do a mean field theory for those, and you can see how they pair. Okay, so that's one way to do it. This state has actually something called a half vortex that has exactly the same properties. Okay? So this state is actually a topological superconductor, which has non-abelian statistics. It was the leading candidate for strontium ruthenate 214. Nowadays, we know it's not, unfortunately. This is nature, it's perverse, doesn't like nice things. And for many years, we all believed that strontium ruthenate had that particular pairing property. Okay, so this is actually to bring closer to the notion of pairing. And I want to end, can I have 5 extra minutes? I want to discuss very quickly the operation of an interferometer and how this shows up in an interferometer. This will be a lightning discussion of interferometers. So this is a so-called Fabry-Perot interferometer in this context, of course. Of course, this comes from interferometers with light. In this context, for the abelian case, this work by Claudio Chamoun when he was still a student. I don't know in what order this is. When on the Wilson, this is 1997 with Nayak, Wilczek, Selek. In 1998, we proposed the non-abelian version of this. I will tell you quickly what they are. We didn't think that anyone was ever going to do an experiment, so we gave just an algorithm for calculating what the interferometer will do. But so we didn't do the simple case for 1/2, which is for n equals 2 in that language. And that was done many years later in 2006 by several people. There is Bonderson. Stengel, and by Stern and Harper independent. This use braiding, this use fusion. These are the dates. Okay, a simple interferometer in this case, in the abelian case, well, all of them look the same, but the question is what do they measure? So you have 2 constrictions in the language that was used by Fev. These are point contacts. Sorry. drawing things. So you have this. This is done with gates and so on. But nothing is localized here, by the way. Okay. And this is similar to things that were discussed actually by Rosenau when he was here. And so you could have tunneling of some quasi-particles here. So you inject some quasi-particle, if you wish, from point A, and then you record what you see here. Typically, what you record is oscillations in the longitudinal conductance. Okay, so if you do a calculation, there will be a tunneling matrix element here, gamma. We call this point 1 and 2, gamma 2. Okay, and there will be a number of quasi-holes maybe trapped here, and there will be some flux. These guys probably are trapped at impurities. So remember that this is a snapshot in time. So here is space. I have my object quasi-particles here. And there are word lines or things like this. So they will not. There will be some process under which they will form knots. So the first quasi-particle can come here, a point say, with amplitude gamma 1 will come here. And the second one will come here and do the same, and there will be a net flux. They will actually encircle them, and so there will be some kind of knot that you will get out of that. Okay, so you end up with an answer for the abelian case. The Laughlin states actually. It looks like, so there is an effective tunneling matrix element that is both of them. There is an Aharonov-Bohm contribution, and there is a fractional statistics contribution. So gamma effective, if you wish, squared looks like gamma 1 squared plus gamma 2 squared, plus a term that is like the real part of gamma 1, gamma 2 complex conjugate. And you get complex conjugate precisely because of the fluxes that they have here. These are complex. So in some function, f that depends on a quantity called omega 0 star, which is the effective charge of these things times the voltage divided by h bar, is like a Josephson frequency. And there is an explicit expression for this. Doesn't matter to us. A is the distance. Yes. It depends on the distance between these guys divided by the velocity of this charge mode. Okay, so it's some expression like this. And this real part has a nice formula. So the real part of gamma 1 star is essentially a number like gamma 1, gamma 2 bar, some effective amplitude, times some exponential here, which is minus I 2 pi. This is for the abelian case. The filling fraction, the flux divided by the flux quantum, I not remember is HC over E, divided minus, so this is the Aharonov-Bohm part. And the fractional statistics is in the next term here, times the filling fraction. And this left was a famous problem that was unsolved experimentally until work done in about 2020 in Manfra's laboratory at Purdue. Actually, he's the last author. I forgot the name of the first author. Okay. So they did the 1/3 and the 2/5, and these are beautiful experiments. Okay, so let me finish. What about our non-abelian friend? This is a much more difficult problem. And Willett has been trying forever to do this. I will tell you later, there's lots of technical difficulties. But I will tell you what the prediction is. And this is what we predicted, and for the specific case for the nu equals a half state is what this. With this, I will end. Sorry for taking more time. So it turns out that there is an even odd effect that, so if you measure, you can measure here the oscillations of the conductors, of the longitudinal conductors. And then in this particular case, for 1/2, for the Moore-Reed state at 1/2, sigma xx is the longitudinal conductors measured there. In the even case, it's just proportional to gamma 1 squared plus gamma 2 squared. Whereas for in the odd case, sigma xx turns out to be more complicated. It's gamma 1 squared plus gamma 2 squared. In other words, there is an additional non-Abelian in that case. And there is an interference term. -1 to the, essentially the number of fermions that are enclosed times the cosine of alpha, which will be the AB phase. This is the AB part of the phase. And there is an argument of 2 over 1, so it includes that. And the part that has the interesting part is n, the number of quasi-holes, times pi over 4. It turns out that doing this computation, in order to do that computation, what you need to do is to compute the expectation value of an ensemble or a group of Wilson loops, which are linked together using non-Abelian Chern-Simons theory. What results is a topological invariant known as the Jones polynomial. And this explicit computation is the reason why Witten got the Fields Medal in 1989. So this piece of junk just measures that, okay? So the oscillatory part, the interference part, measures just the Jones polynomial, which is a topological invariant of this collection of the histories of the quasi-particles. That's really what it measures.
So I suggest that we.
And this, with this, I end.
Excellent,
Okay.
thank you, because this is a very beautiful and very complicated thing.
Yes.
I think if we get into this now, we're going to spend the next half an hour explaining what this formula means.
Which is not what I wanted to do. That's why I wanted to just flash it for you. Okay?
Exactly.
I didn't
So-
present in particular our algorithm and any of that.
But you get another chance with Eduardo this evening at 6:30.
Yes.
And so you can grab him then and ask him to explain this formula.
Good.
So any questions?
I think I overwhelmed everybody today. Maybe it was totally obscure, but well, I wanted to give you a flavor of what this actually entails and why these things are topological and why we like them. There is actually a state that has, if the 12th state is a so-called Fibonacci state, maybe we can even make a universal quantum computer with it. But again, we don't even know if it is the right state.
One question. So here, when you are discussing a Fabry-Perot interferometer, now it's
Sorry?
in the Fabry-Perot interferometer,
Yes.
you don't have this contact which is sitting in the middle,
Well, you do.
like the.
No, you do. There are always a number of quasi-particles here, except that in the Abelian case, these are our friends, the Laughlin quasi-particles.
Yeah, that I understand. But I'm saying that when I go to the Mach-Zehnder interferometer,
Right?
in the Mach-Zehnder interferometer,
Yes.
you have this extra gate that that sits inside that picks up also in a very different way. And this quasi-particles.
I'm not discussing Mach-Zehnder here, okay? But you can do the same construction.
My question is, you also have an odd even effect there?
Yes.
The odd even effect.
It's always there. That's simply because the important part, the oscillatory part, whether you use Mach Zehnder or you use this, is given by this expectation value that I just mentioned. And in one way or the other, you get that. The difference with Mach Zehnder is that it doesn't depend crucially on the area of this and all of that. And that's a technical difference. From the point of view of the fractional statistics, it's the same.
Other questions?
Okay.